And in this video, we're going to compare SN1 reaction and SN2 reaction from the perspective of mechanism. SN2 reaction usually undergoes with primary or secondary alkyl halide. For a tertiary alkyl halide, you almost only undergo SN1 reaction only. And SN2 reaction is a one-step mechanism, but that one step includes two molecules, so it's called a bimolecular rate. SN1 reaction actually happens in two separate steps, and each step there's only one molecule involved, so it's called unimolecular rate. In the SN2 reaction, there's a possible steric hindrance which will make it go slower, but it does cause an inversion of the stereochemistry. Where in SN1 reaction, you're going to have a very stable carbocation intermediate with, or in other words, a carbon with a positive charge. And that's partially why tertiary carbon prefer to carry positive charge or SN1 mechanism. And because of the carbocation intermediate, you may have a racemic mixture, or in other words, the stereochemistry is undefined. The rate law of the SN2 reaction will be rate constant, alkyl halide and nucleophile multiplied together, whereas SN1 reaction has only to do with the alkyl halide. Now let's take a look at the mechanism of each one using the energy diagram. Now these are a couple of energy diagrams for SN2 reaction. You can see in the top left one, there is one peak, which means in the energy diagram, the energy is on the y-axis and the reaction progress on the x-axis. On the very left, you have the reactants, starting energy up here, and the products ending final energy down here. So in other words, regardless what kind of reaction this reaction is going from a high energy reactant to a low energy product. So this reaction is losing energy. In other words, this is going to be an exothermic reaction. On the other side, you're going to see if you started with a relatively lower energy reactants to a higher energy product, regardless what kind of pathway you're going through, your overall energy is gained. So this is an endothermic process. To both reactions here, to both mechanism here, they both are going through one peak. Now, every peak in energy diagram shows you a one transition state. Now, in SN2 reaction, the transition state is down here. So it's a bimolecular mechanism. The carbon in the middle that used to be bound with the leaving group, but the leaving group will be leaving, taking pair of electrons. At the same time, nucleophile will come in to attack this carbon with another pair of electrons. So you can see this carbon at the transition state currently is under sp2 hybridization, with the other three substituents on the carbon, in this case shown as three hydrogens, are going to be in the perfect triangle plane shape. And while leaving group leaves at the same time, and while nucleophile attacking at the same time, the dotted line meaning partially broken bond and the partially formed bond. So this transition state is basically the only transition state in SN2 reaction. And of course, the energy peak here between the reactants and the transition state between peak, this is the activation energy. And then below the activation energy, the difference between the reactants and the product, the energy, that's the enthalpy of the reaction. And the right one is the same. Between the products and the reactants, this energy difference is the enthalpy change of the reaction, delta H. But from the reactants to the top of the peak, that's the activation energy. Now for SN1 reaction though, something are similar. For example, the enthalpy change of the reaction are going to be defined the same. From the reactants to the product, in the left one, you have energy going from reactants down to products. So products has lower energy. So this delta H is going to be negative, and that's an exothermic process. And the right one, you can see the reactants has lower energy. The products is up here. So the enthalpy change is actually positive. going up. So this is endothermic process, simply because product has higher energy than the reactant. On the mechanism-wise, there are two peaks on both diagrams. And notice that the first peak is always higher than the second peak in the same diagram. So you can see them in the first one, this peak is higher than this peak. In the other diagram, you can see the first peak is higher than the second peak, both indicating that the first step or the first transition state is the rate limiting step or the slower step. The second transition state or the second step is the relative faster step because of the relative lower activation energy. Sorry. And the first valley, there's one valley in between two peaks on both diagrams. That's the intermediate. So what we should be able to draw out here is, first of all, from the reactants to the first peak, that's the activation energy of the entire reaction, because that's the higher one. So we don't have to look at the second activation energy. The first activation determines how fast, how slow this reaction will be. The first transition state is when the alkyl halide, here represented by R, L. L is the leaving group, R stands for the alkyl group. When this bond breaking first, so the first transition state, which is the transition state A, notice that transition state is always going to be square bracket with a symbol, double cross symbol. Now substitute A representing the first transition state. You can see here this carbon, which is where the leaving group used to attach to, because of the electronegativity difference. So this carbon has relative partial positive charge, and leaving group has partial negative charge. Because this carbon is a tertiary carbon, and we already said that tertiary alkyl halide prefer to undergo SN1 reaction. So this carbon is okay to carry a positive charge. So the leaving group is okay to leave with a pair of electrons. Now this partially broken bond shows the first transition state number 1. Now after this leaving group completely left, that will leave you a carbon with a positive charge, which is called carbocation. Carbocation is basically this intermediate, which shows relatively lower energy in the valley down here. Now, the carbocation with a positive charge will be attractive to the nucleophile. So the second transition state will be caused by when the nucleophile trying to approach the carbocation, providing a pair of electrons. So the partially formed bond between nucleophile and carbon forms the second transition state, which is transition state B, or the transition state number 2, shows here on the second peak. And then after this nucleophile carbon bond is completely formed, you'll get the product, which is, you can see here, nucleophile and R group are completely bonded together with a free leaving group. Now, the progress undergoes almost exact same in the right one, endothermic one. First of all, the reactants, the alkyl halide leaving group leaves, forms the first, that in the progress of leaving, you're going to have first transition state. Until it's completely, after it's completely left the leaving group, you're going to have R plus, first carbocation, intermediate. And this intermediate carbocation, which is a positive charge of the cation, will be attracted by the nucleophile, forming a nucleophile carbon bond. That's going to be the second transition state. And when the second transition state is completely formed, you're going to have the product, which is a complete bond between nucleophile and R. So basically, the substitution is basically replacing the leaving group with a nucleophile. Now let's take a look at a few examples, see if we can analyze the several reactions down here. You can pause the video here, see if you can try to answer the questions. Now in this reaction, consider the exothermic nucleophilic substitution reaction up here. First of all, it tells you it's exothermic reaction. So it's going to ask you to draw energy diagram. Okay. So the energy diagram is going to look like energy. Then the reaction progress. Because it's exothermic, that means the delta H is going down. You're releasing heat. So we can assume that reactants is here, product here. This is not a quantitative analysis. So reactant, product. Now look at the alkyl halide. This is a primary alkyl halide. This is a nucleophile. Primary alkyl halide undergoes SN2 reaction, which means the mechanism is going to be the cyanide will attack this carbon, and this chlorine will leave at the same time. So forming a transition state, which is going to be 3 carbons. This carbon is going to be partially bonded to Cl, at the same partially bonded to Cn. Leaving group and leaves and the nucleophile attacks at the same time. So this is going to be SN2 reaction with only one transition state, one product, which is going to be the same structure except replace Cl with Cn. So we're going to draw an NH diagram with only one transition state, which is going to be one peak, and going down to the product. Where the peak is going to be the transition state. You can simplify as Ts. The energy difference between the reactant and the transition state is activation energy, EA. The energy difference between the reactant and the product is the enthalpy change of the reaction, which is delta H. Now, the product's reactants is propyl chloride. The product is propyl cyanide. The transition state can be drawn here. I think we answered all the questions. We draw the energy diagram for the reaction. We label the axis X and Y. We show the word delta H. We label delta H EA. We draw the structures and the transition state. We can draw the mechanism of the reaction using arrows to show electron flow of the movement. You can pause the video here to see if you can try this out. In this reaction, you're having a tertiary alkyl halide. This is a tertiary alkyl halide. So that guarantees you this is going to undergo SN1 reaction, not SN2. Because it's undergo SN1 reaction, so this is going to be a two-step mechanism. But at the same time, question also tells you this is an exothermic reaction. So we're going to draw the energy diagram. The y-axis is going to be the energy. The x-axis is going to be the reaction progress. The first thing you can determine already is exothermic. That means the reaction is going to lose energy. The enthalpy change is going to be going from higher energy reactants to lower energy product. This is because of the exothermic. Now, because it's a tertiary alkyl halide, so it's guaranteed to have SN1 reaction, which means there are two steps. Every step, there's only one thing involved. In the first step, the the leaving group leaves. Now the transition state will look like the leaving group leaves partially. So this is transition state A. And then after leaving group iodide left, which is minus iodide, you're going to have the first intermediate, which is going to be a positive charged carbocation. Notice that we use the square bracket to cover the transition state, but we didn't use that for the intermediate. And in the presence of nucleophile, which is methyl sulfide, the methyl sulfide, CH3, will be able to attack this carbocation positive charge because of the electrons on the sulfur. So that's going to form the second transition state. The bond is partially formed between sulfur and this carbon. Of course, there's a methyl group on the sulfur too. That will be the second transition state. Transition state B. And of course, the product will be formed by connecting this carbon with the sulfur and the methyl group. Now I need to highlight transition state A and transition state B. In the energy diagram, we should be able to construct two peaks. The first peak, and then go down to a valley, and then second peak. But the second peak is always going to be lower than the first peak relatively, and then go all the way to product. I think the going downhill should be more smoother than this. So this is reactant to start with. And the first peak here is going to be transition state A. And second peak here is transition state B. On the y-axis, the height difference between transition state A and the reactant, that's going to be the activation energy of the entire reaction. The valley between two peaks is going to be the intermediate carbocation R+. I think we'll draw the energy diagram. We indicate this is SN1 reaction. We labeled X and Y axis. We also show the enthalpy change and the activation energy of the reaction on the energy diagram. We draw all of the structures, which including the arrow of showing the electron flow in the reaction mechanism up here.